Okay, hey everyone. So this is the laboratory video for the week 9 lab that you're marking in week 10. Very good. This is the second last lab. Next week is the last lab. So nice work making it through so far. Nothing really has gone wrong, which is good. But, marks are about to be calculated and entered into the Moodle. So hopefully nothing else goes wrong. Anyway, I'm going through the questions. There are 2 questions, but each question is now out of 2. Because, I don't know, I felt like it. In next week, there's only 1 question that's out of 2. Just kind of, I don't know, weird it up a bit. I wanted for once a lab that you couldn't pass without doing these questions. So here we are. And it's my favorite lab, microwave optics. Question 1 is your really, really simple polarizer Moodle thing. 2 polarizers, 90 degrees to each other, no light go. Third polarizer at 45 degrees to the 2 of them. In between, light do go. Explain. So 2 parts. 1, explain why. 2, what would happen if we took polarizer C and put it here at the front or here at the back? Answer to part 1. Basically, you could just say Males's law, right? Like it get cos squared 45 here and cos squared 45 here, and cos squared 45 times cos squared 45 is not 0, whereas cos 90, or cos squared 90, is 0. They can just like formula it or like verbally explain it any other way. That works. And then what would happen if polarizer C was placed at the start or end? You'd still get no light through, right? Because there'd be 2 polarizers at right angles to each other. No matter where you put this third polarizer C at the front or the back, it doesn't matter. It's going to not let any light through, right? So those are the answers, right? So some sort of Males's law explanation, and wow, no light through because Males's law. Anyway, whatever, that's the easy one. The next one. Oh, that's a picture of my face. I hate the thumbnails that YouTube makes of all my videos. It's really dumb. Also, in the lab for week 10, I'll tell you later. I put a little joke in there. Anyway, this is the next question. I like this one. So this is something has gone wrong with your experiment. Explain what the outcome of this gone wrong would be on your results, and explain how you could fix it without taking data again. And the second part's much less important, right? So essentially, there's an error that's happened. They have to pick one of these. And really, what I want to be seeing is them outlining how any assumption inherent to the experiment is no longer true. So this I copied this question from Special Physics that I wrote to, so don't worry, I'm not plagiarizing. Because this is kind of an opportunity for students to flex in terms of how well they understand what's actually going on in systems. And I'll walk through the errors, and then I'll talk about what kind of the answers I'm thinking of are. Just going to move a thing. There we go. Oh, no. Okay. I'm just moving a thing so I can check that this is recording, because that would be good. Anyway, error 1. Your lab partner has set the experiment up the wrong way. They're rotating the arm containing the transmitter instead of rotating the arm that contains the receiver. So what's supposed to happen in this lab is they're supposed to have the transmitter here, and then they rotate the receiver. So the transmitter goes here. It's a double-slit interference pattern. Probably should have specified that. This is a double-slit interference pattern experiment with a microwave system. Otherwise, you're just seeing like this question. Anyway, and obviously it creates the ye olde sync squared, the old sync function, whatever. You know the thing. It creates the double slit pattern, and then you measure the double slit pattern angle by angle by moving this detector, right? And kind of a lot of assumptions are made here. The main assumption is that it's a plane wave coming in, and so these 2 parts are perfectly in phase, and also that essentially that this is like a little cone, or loud flower as we call it in the business, and it kind of has like a finite divergence, which means that if you put it like right up against there, it's just going to be blocked by the slit, blocked by the opposite of a slit, the blocker, the anti-slit. Is that a thing? Theorists, let me know in the chat if anti-slit is a thing. Anyway, so your lab partner accidentally moved the wrong one. This is inspired by a true story, i.e. like half the kids who do this experiment. They rotate the transmitter arm instead of the receiver arm. They still measure angles, but the angles are technically the angle of the transmitter instead of the angle of the receiver. So what's happening here, right, is when they rotate this, there's kind of, I want to emphasize, a valid answer is the correct answer. There isn't the correct answer for any of these, but a valid answer that kind of approaches the problem in a physicsy way is the correct answer. That's all I'm looking for here. So the answers that I like to see, at least, is a student could assert that there is no difference because if you do like a single path length calculation, the path length, like for example, the position of the maximas may not be different. If you calculate path length difference and do all that sort of stuff, that they could argue that there is no difference, right? Which is okay. They could argue that the pattern would be distorted, right? Obviously, the assumption that's being violated here is that the two waves are arriving perfectly in phase and at the same intensity, right? So ideally, when this system leaves here, these two waves should be arriving in phase. We're assuming that the slits are thin enough that the incident direction of the wavefront doesn't matter, but they could talk about that, right? Because obviously, as A gets smaller and smaller, as the slit size gets smaller and smaller, the incident angle of the Madoodle, the wave, matters less and less as it kind of diffracts itself out in a bajillion different directions. But they could argue, the slits are probably big enough that the incident direction does matter. So that would be another one. And then you get a weird skewed pattern, right? Like you get a pattern, if it was kind of transmitting this way, you get a pattern that's skewed this way and you wouldn't get nice data at all, right? Because you'd have a skewed wavefront and it'd like affect the way it diffracts. So there's a lot of options, really. Anything that physically seems to be valid. And as always, just pop in the chat if on the chat, the Teams thingy, if you got any questions, or if you don't know which ones are valid or not. If you got an idea, if your student says something dumb. Now, that said, most people mark like Sunday night. So yeah, I don't know. Use your own judgment. If it's 9 p.m. on a Sunday, I'm not. If it's 9 p.m. on a Sunday, I probably will read it, but I don't want to. So don't. All right. Lab partners put the transmitter very close to the double slit, but everything else is correct. Oh, sorry. How can you fix it, right? So that's how would you attempt to correct for this mistake without retaking data? Most of them, essentially, their answers will depend entirely on what they've decided has gone wrong or what they decided the outcome is. And almost all of the answers will be either, it should be still okay to find the points of maxima or something, even if maybe the intensities aren't correct. Or, my data is screwed. Or, I have to have a new experiment now that essentially validates a different principle. Like Lamau, this one's not that important, but I just like to make them think about it. The most important one is analyzing which assumption is violated and talking about how the results are different. So transmitter very close to the double slit. I mean, the easiest one that violates is obviously that the source is not, like the distance between the source and the slits is not very, very big relative to the displacement between the slits, which is an assumption that we need for, I'm not going to say it's far field diffraction, but for far fieldiness, I know I have a PhD in optics, so I'm allowed to say that. Anyway, what's the actual point? So some students just say that, and then that's okay, right? That's good enough. Other students will say, okay, well, it may have not have become a plane wave by this point, right? Because obviously we like to assume an infinite distance because we want the incident wave to be planar. And, well, we want the incident wave to be planar because we want to assume that the incident phases are the same, the incident intensities are the same on both sides, and the incident directions are the same on both sides if you have decided that direction matters. Again, it's very dependent on the slit width. If they, get into talking about how the slit width affects how, the diffraction direction, just give them the marks anyway. That's enough thinking. That they are on, they're already well beyond what we need to concern ourselves with. If they mention Heisenberg's uncertainty principle using diffraction, I know it's not a thing, but it's kind of like a fun real life physics example, because quantum physics isn't real physics. Don't at me, quantum physicists. Anyway, where was I? I don't remember. Anyway, a plane wave. It's not a plane wave. Yeah, it's not a plane wave. That's the one. I'm not taking another take of this. So it's not a plane wave, Lamau. That's problem number one. Option number two, it is so close to the slit that you can't get any EM wave. So close to the blocker that there's no EM wave through the slits. It's fine too. You can just say, hey, it doesn't spread out enough, or it spreads out so little over the distance that there's negligible power through either side, and you get really low values. That works too. So that's a good one. Number three, the transmitter now emits a range of frequencies. Now I goofed. I accidentally wrote megahertz instead of gigahertz initially. One student was like, actually, sir, if it was megahertz, the wavelength would have changed so drastically that the experiment wouldn't work. And I was like, yeah, you got me. Which is now good on them, right? And then they asked, so are you writing a trick question or did you just misspell? The answer is I misspelled. So if a student talks about how you dropped the microwave transmitter and it turned into a radio wave transmitter, technically they are right because that's how I'd written it initially. But let's go from here. Basically, now there's a bunch of wavelengths. The diffraction patterns, you just have a bunch of diffraction patterns kind of smeared all over each other. So they could kind of talk about this one of two ways. They could say either it's just a big blob now. Like if they decide to put in numbers and say, okay, the 10 gigahertz N1 angle is this, the 11 gigahertz N1 angle is this, like for the angle of the first maxima, and actually assert how much of a difference that makes. Beautiful, phenomenal, amazing. If they just say, hey, the peaks are fatter now because obviously there's a wider range of frequencies, that's also fine. If they say like convolve, that would be nice, even though it's not really a convolution, but whatever. And then what do you do about it? Well, you just kind of deal with it. Ideally, I mean, you could kind of take the entire data set at really fine angular increments and then attempt a deconvolution if you knew the actual spectrum of frequencies that came out of this thing. If they say that, please just refer them to me because that's cool. But the usual answer is you just take the middle of the peak, right? Because we're only looking for the maxima and the minima anyway. And so I forget what frequency is supposed to be. Okay, it's supposed to be 10.07, so you don't take to the middle, but whatever. Just do some sort of data processing and figure out where the peaks are that way. There you go. So those are the three. And so it's out of 2. I would give them 1 mark for also some of them pick all 3. I don't know why, because I wrote do 1 of them. But if they do all 3, just mark 1 of them, right? They don't get extra marks for doing all 3. Right, although you can pick the best one if you want, right? If they did 2 of them really trash, you just pick 1. Anyway, give them 1 mark in this for essentially outlining what's up, right? What's gone wrong in terms of what assumption is no longer violated. I've written the most useful piece of information for each question will be what assumption based in this experiment is not true. So if they don't include this information, just lose a whole mark. Like, come on, learn to read. And then second mark is for kind of the practical. Okay, this is what would happen and this is how I'd fix it. So there you go. So that's that. So I went for too long on this one, so I'm sorry. Yeah, I don't know. Have a good day.